Greetings, Calculus 2 students, and welcome to this Going Deeper video on the partial fractions theorem. So one of our major suites of integration techniques have to do with evaluating integrals of rational functions. There is a lot of behind-the-scenes background that goes into that, and what we'll do in this video is we'll take a peek behind those scenes to see some of the theory behind what makes these methods work. This is the kind of stuff that we cannot really delve into in class due to time constraints, but I hope to give you some ideas of sort of the complexities and the powerful results that are behind allowing us to integrate rational functions. So first, some review just of the basic concepts that are involved here. First of all, in order to talk about rational functions, we must first know polynomials. And a polynomial or a polynomial function, well, let's stick with one variable here, as we tend to do in initial calculus. So a polynomial in one variable is a sum of constant multiples of power functions with non-negative integer exponents. What often throws people off in understanding what a polynomial is and is not is this idea that the exponents must be non-negative integers. So the exponents have to be numbers like 1, 2, 3, and so forth. You cannot have negative exponents. You cannot have fractional exponents or an exponent of pi or anything weird like that. They can only be non-negative integers. And then the degree of the polynomial is just the highest exponent that you see on any variable. Now, we'll see coming up in our work here two special types of polynomials based on their degrees. A degree 1 polynomial is typically called a linear polynomial, and a degree 2 polynomial is called a quadratic polynomial. Again, a lot of emphasis in modern mathematics on functions. I think that's a little overdone, but nonetheless, in all these things, we could be talking about functions. I'll tend to more often talk about expressions, I think. Sometimes we may say, oh, we're integrating a function or something like that too. So a rational expression then, or if you like, a rational function, it's just an expression that can be written as a quotient of two polynomials. So the general form of a rational function f would be that f of x equals p of x over q of x. Its formula can be written in that form where p of x and q of x are polynomials. And these are the types of expressions or functions that we want to be able to integrate. And with a few caveats, we can integrate rational functions. There is some aspect of, in theory, we can do this. In practice, there are some difficulties that can arise. But in many, many cases, the kinds of cases we'll come across, we are able to integrate rational functions. And how are we able to do that? Well, the real hero behind the scenes here is the partial fractions theorem. This is the key result that really allows all these techniques to work. The partial fractions theorem, and this is a theorem from advanced algebra, certainly not the kind of thing that we're going to examine in depth in this course. It's way beyond the scope of calculus. But here's what the theorem says. It says that any rational expression can be broken down into a sum of the following three types of terms. Well, one of the types of terms is a polynomial, and the other two types are rational expressions, but they are rational expressions of very specific forms. One of the forms is a over p plus q to the m, and again here the presumption, as usual, is that x is the variable, and everything else here is a constant. You'll see here, yeah, so capital A, B, and C, lowercase a, b, and c, and p and q, all of those are constants, that is to say, real numbers. We're working with real numbers as our basis here. Okay, and then the other form that terms can have is that they can look like bx plus c over ax squared plus bx plus c to the n. Now, this is great news because all of these are types of expressions that we can integrate. Polynomials, very easy to integrate. If we have a constant over a power of a linear function, that is also pretty easy to integrate just with a little bit of substitution. And the third type of term, now there are a few complications that can arise with the linear numerator over a power of a quadratic denominator, but nonetheless, those should be doable as well. And so the great thing is that this allows us to take whatever rational expression we have and rewrite it in a form that we can integrate, which, as we know, is the goal of all integration techniques, is to get the expression rewritten to where we can evaluate it. Okay. Now, that third type of term, the one that I mentioned as being relatively trickier compared to the other two, a lot of times you don't even need that. Where it does come into play is if you get an expression of the form ax squared plus bx plus c that cannot be factored into a product of two linear polynomials. And that happens, how do we know when that happens? Well, it happens exactly when the discriminant b squared minus 4ac is negative. Negative discriminant for a quadratic polynomial means it cannot be factored. So that's something you can look at to see whether your factoring needs to go any further. Okay, in nice situations, you are able to get down to linear factors, and then you only need constant numerators, which is even nicer. Okay, so let's look at one setup of an example that kind of illustrates how there can be some challenges and difficulties even working with this nice partial fractions theorem. So with the example that we're going to look at, and with any example like this, the first step is always going to be to factor the denominator. Now, in theory, we can factor any polynomial into a product of linear and quadratic factors. There's a theorem that says that as well, and I guess indirectly, the partial fractions theorem tells us that as well. There are some facts that will help us with factoring, although, truth be told, factoring can be a real monster sometimes. But it should be doable in the types of examples that you see. Here are some facts that can help you factor a polynomial. For one thing, it has to do with linear factors and roots of the polynomial. So when f of a is equal to 0, we would say a is a root. So this is a root theorem. It says that x minus a is a factor of polynomial f if and only if f of a equals 0. So the direction here that is useful to us is that if we can find a 0 or a root of our polynomial, let's say that root is a, we then know that x minus a has to be a factor of that polynomial. And while that may not do the whole factoring job for us, it certainly allows us to get started in a way that we'll see. Another fact that comes in handy sometimes is that if you have a polynomial, if it does factor into linear factors entirely, n linear factors if it's degree n, then, which is the nicest case, which you kind of hope is going to happen, then the constant term of that polynomial is possibly plus or minus. There's a negative 1 to the n factor in there. But more or less, it is the product of the roots of the polynomial. So if you're looking for roots, let's say you want to apply fact 1, you can look at that constant term and say, well, I hope that my roots are going to be factors of this constant term, and that's just optimistically hoping that your roots are going to be integers, which again, in kind of nicely packaged textbook problems, that tends to be the case. All right, so let's take a look at the following example. So here is a rational expression, 5x to the fourth plus 9x cubed plus 47x plus 100 is our numerator, and then our denominator, also a polynomial, is x to the fifth plus x to the fourth minus x minus 1. So we have a degree 4 polynomial over a degree 5 polynomial. We want to form the partial fractions decomposition of that, which means we want to write it as the sum of terms of the type that we see in the partial fractions theorem. Okay, now the first thing we have to do is, the denominators only are linear or quadratic. So to start off, we need to be able to factor the denominator. And that denominator, it's a degree 5 polynomial, not necessarily the easiest type to factor. And truth be told, there are going to be some polynomials that, practically speaking, you really can't factor them. This one we could do, and we'll take a look at a couple ways to do it actually. We'll start by looking at a way that uses mainly fact 1. We don't really need to bring in fact 2 too much this time. So we'll mainly use fact 1 here and look for roots of our polynomial. And then there's another way to do it. Second way is easier. You may wonder why we went through doing it the first way after you see the second way. But again, both of these really, they're kind of specialized methods. Even though they're powerful ones, they only work in certain situations. So let's see how that plays out. Okay, so for method 1, here we're going to look for roots. So method 1, we want to find roots and then use those roots to get us going in our factoring. Okay, so one thing to notice is that if we try to put in x equals 1 here, if we do that, we're going to get 1 plus 1 minus 1 minus 1, that is 0. And so that tells us that x equals 1 is, maybe if it'll write here, yes, is a root. Okay, and because of that, I'll make an arrow going this way, that tells us that x minus 1 is a factor. That's due to that fact 1. Okay, so we know that x to the 5th minus x, or plus x to the 4th minus x minus 1 is going to equal x minus 1 times something. Now, what's that something going to be? That's the real question. Well, we can figure this out, working at it step by step. We know it's going to be degree 4 because we need an x to the 4th here. That then gives us, when we multiply, it will give us an x to the 5th. That's great. And then we will also get from this a minus x to the 4th, but we don't want minus x to the 4th. We want plus x to the 4th. So what we can do is add a plus 2x cubed here. Now, in addition to our minus x to the 4th, we will get, when we do first term times second term here, we will get plus 2x to the 4th. And overall, that will give us our plus x to the 4th that we want. Oh, but then we're also getting a minus 2x cubed. We don't want a minus 2x cubed. In fact, we don't want any x cubed term. Or in other words, we want 0x cubed. So what we can do here is we can add in 2x squared. Okay, let's see if that works. Now we are going to get our minus 2x cubed. And then when we do first term times third term, we will get plus 2x cubed. And those will cancel out so that we get no x cubed term. All right, continuing along that path, we can add 2x because we do not want to have an x squared term either. Now we will have minus 2x squared, yes, but we will also get plus 2x squared. And those will cancel out as well. Okay, now, what else? We get a minus 2x. We want just a minus x, so we need one more x added back in there. And I feel like, let's see, maybe a minus 1 is going to do that. Let's find out. So now for our x terms, we have minus 2x, and then minus x. That will give us minus 3x, not what we want, so maybe this better be a plus. Okay, so now we have minus 2x plus x. Sure enough, that gives us minus x. And then when we multiply the constant terms, we get minus 1. So great. We have a start to our factoring of this polynomial. Now we can do the same kind of thing again. I will just leave the details for you to check here, but x equals -1 is now a root of the polynomial we have left. And again, how do you get these? Well, you just kind of do trial and error to some extent, but remember that you're also looking at factors of your constant term. Constant term's 1 here. It does not have a lot of integer factors, but it can be -1 times -1. And so -1 is a great place to look. And sure enough, it turns out to be a factor. So that tells us then, if we keep on going here, let's maybe continue on down this way. This is going to equal, it's also going to have a factor. Yes, we have the x minus 1 factor, but now we have x minus -1 as a factor. That's x plus 1. Okay, so now going through that same kind of process that we went through before, we're going to have an x cubed here. And let's see, I think we're going to also get an x squared, because now this will give us x cubed plus x cubed. That's 2x cubed. We'll get an x. Again, you can pause at any time here and think through the details more. It does take some thinking, no doubt. We get x squared plus x squared, which is 2x squared. Okay, we now get x plus x, which is 2x, and then constant term 1. Okay, so now the next question is, what about this x cubed plus x squared plus x plus 1? We factor that further. Well, we know it has to get down to at least a quadratic. And you can check that x equals -1 is still a root. Okay, so that means we get another factor of x plus 1. And going through that same process again, to get x cubed, we need x squared. We will get a plus x squared, which we already have. And now we need a plus x and a plus 1. Well, just adding a 1 here will give us a plus x and a plus 1 when we FOIL that back out. And so there we go. And now we're down to, we got 3 linear factors. We got a quadratic factor. Can we factor that quadratic further? Well, you may try it, and you may not be getting it to work out. And of course, that could be because you're just not finding the factors yet, or it could be because it cannot be factored. And the thing to look at here would be b squared minus 4ac. Now our b here is 0. There is no linear term. And so this is just going to be -4 times 1 times 1, which is -4. That's less than 0. That tells us that that quadratic cannot be further factored. So there we go. We actually have our factorization of the polynomial, which is just like this. Okay, now let me show you method 2, which again may appear to be quite a bit easier in this particular instance, but again, a very specialized thing. And method 2, what we can do is we can factor by grouping. We can put the first 2 factors together like this, x to the 5th plus x to the 4th. And then we can think of this as adding plus -x minus 1. And we can recognize that, hey, these first 2 terms, if we group them together, which I should put parentheses around them, I can factor an x to the 4th out of there. And then I've got just x plus 1. And the last 2 terms, I can factor a minus sign out. And I'll just have x plus 1 there. And lo and behold, we now have x plus 1 that is common to both terms. And so we can factor that out, and we're left with x to the 4th minus 1 times x plus 1. Okay, now it gets easier in the sense of if you look at that x to the 4th minus 1 and recognize that as a difference of squares, that can be factored as x squared minus 1 times x squared plus 1. We still got our other x plus 1 there. And then x squared minus 1 can be further factored into x plus 1 times x minus 1. And the other terms were already fully factored, so we'll just leave them there. And you can see that here we have the same factorization. The order is different, but again, the factors are all the same. Okay, now probably one more way we should rewrite this is we have x plus 1 there twice. So really that is, yes, we got x minus 1, but we also have x plus 1 squared. That square tells us something important about what the decomposition will look like. Okay. All right, so we've got our factorization. Let's see if this will appear. Yes, okay, there it is, although, okay, I'm going to end up blocking something here. Okay. All right, so because of this squared factor, we are actually going to need two terms in our decomposition for that, and we'll provide more motivation for that in class. I'll say a little bit about it now here too. Okay, so we need two terms because that factor is squared. Whenever you have a power on a term, you need one term for each, up to the power that you have there. If we had a cube, we would need three terms and so forth. So our partial fractions decomposition then is going to look as follows. So here is our partial fractions decomposition. I'll just abbreviate it. And this is just going to be the form of it. There would still be more details to work out, which we're not going to work out for this example. But it would be that 5x to the fourth plus 9x cubed plus 47x plus 100 over x to the fifth plus x to the fourth minus x minus 1. Okay, so partial fractions decomposition, we know for this x minus 1, we are going to have a constant, which we'll denote as capital A for now, over x minus 1. We also will get a fraction that has a constant, which we'll call b in the numerator, over x plus 1. That comes from this x plus 1 part of the factorization. And then we need another one for that. So we'll use a capital C over x plus 1 squared. Okay. Again, people often wonder, how come we need two there? Well, basically, in a nutshell, the reason is that we want our numerators to be constants. Okay, if we did not have two terms for that, the most we could guarantee, the best we could say is that our numerator would look like bx plus c. It would be linear. We want those numerators to be constant if we possibly can have that, because again, that will grease the skids for our integration when we try to integrate this thing. And then finally, we have our quadratic factor, x squared plus 1. Okay, so we get another term for that with that factor, x squared plus 1, in the denominator. And for a quadratic factor in the numerator, we cannot guarantee that it's going to be just a constant. It may be a linear polynomial. And so we'll represent that with arbitrary coefficients, d and e. It will have the form dx plus e. Okay, and there we go. That is our form of the partial fractions decomposition. Now, in general, of course, this is a very complicated one to do. But if we were going to fully complete this, we would still have more work to do, because we would still need to figure out exactly what those constants A, B, C, D, and E are. But we're not going to take it that far with this example. I just wanted to give a feel for how the partial fractions theorem kind of interacts with setting up what this partial fractions decomposition is going to look like. Again, lots of details involved there behind the scenes. In class, we will very much gloss over these, but if you wanted to know more of how this really all works, these are some of the nuts and bolts of it. Hope you enjoyed the video.